Good morning, everyone. So it's an honor and a pleasure for me to be here at the summer school in Gdansk. The weather is perfect too, but it seems it will change, but I'm leaving, unfortunately, tomorrow morning, so I'll take the sun with me. Okay, what I'd like to talk about today is I'd like to focus on two topics. It's accelerating machine learning and how with RAPIDS and with DGX-2. Both of these keywords I'm going to go into detail within my presentation. So, please let me introduce myself. For those who don't know me yet, my name is Ralph Hinche, and I'm a business development manager at NVIDIA, basically responsible for interacting with customers in higher education and research, so responsible for universities, for the universities of applied sciences, and also the big science institutions like Max Planck, Fraunhofer, Helmholtz, or Leibniz societies, and responsible for, well, I would basically say half of Europe. So before I go into the details of my presentation, I'd like to motivate you, as this is the lecture today, I'd like to motivate you with a short video explaining and showing what NVIDIA is doing with real-world projects in terms of deep learning and machine learning. So enjoy the next 3 minutes, please. I hope you enjoyed it. Just to show you a few real-world projects we're working on together with our customers. I really like the idea about the flying boat. I think that would be perfect here for Gdansk with the water you have here. That would be a perfect way of getting around. Okay, let's go back in history a little bit. It's now 13 years we're involved in GPU computing. So basically in 2006 was when we introduced the first CUDA library. So the first library for interacting with our massively parallel CUDA cores. And it's basically in 2012 we had the renaissance of AI. This is when the AI hype started and took off with the ImageNet competition, where Alex Kruszewski showed how to deploy deep learning to basically beat every other algorithm in terms of object detection within images. And this is actually also when we invented and distributed our first CUDA DNN library. So it's 13 years of GPU computing, and it's 7 years of NVIDIA supporting AI, basically. So the ecosystem, it's not only about hardware. It's not only about hardware. To deploy a hardware efficiently, you need a full ecosystem supporting it. And this slide actually gives a good overview of what is involved in this whole task of accelerating AI. On the bottom side, of course, we have the hardware needed. Basically going from the Tesla, the professional GPUs, over our dedicated DGX AI appliances, of course also HGX appliances of our partners, and also our cloud partners, where you can actively tap into these accelerating resources within the cloud. And on top of that, you of course need core libraries. It's our CUDA and core libraries with cuBLAS, and the Nickel libraries, which are the communication libraries to effectively accelerate multi-GPU and multi-node applications. So if you're going beyond the scope of a single GPU, you need a very efficient network of transferring data between the GPUs and accessing distance data if you're going multi-node, of course. And on top of that, we have our dedicated libraries. In terms of deep learning, the first ones we invented and distributed were, of course, CUDA DNN. That one is 7 years old now, and we've advanced it to a very mature state and we're achieving more performance and more performance every year. So even if you stay on the same hardware, you can be sure that with the advances we make in our libraries, you'll be seeing very large steps forward in performance from year to year even then. And what I'll be talking about today is what we're doing in machine learning. We started with supporting deep learning 7 years ago. In terms of machine learning, we're supporting that since 1 year now. And I'm going to go into these specialized libraries you see here, so CUDA-DF, CUDA-ML, and CUDA-Graph, and I'll explain what they do and which acceleration values you can expect. On top of that, you have, of course, the applications and frameworks. So all popular deep learning frameworks are supported out of the box. They use our CUDA-DNN library. There's basically no leading deep learning framework which does not support our GPUs. And so if you're using Python, TensorFlow, MXNet, PyTorch, or other leading frameworks, you can be sure that there's going to be a support for our architecture. And what I'm going to talk about today, and this is the second thing, it's RAPIDS. What is RAPIDS, and what is included in RAPIDS, and how can RAPIDS help you to accelerate your machine learning applications. So our platform is the most adapted platform for accelerating AI. We've been doing that since 7 years, so it's a very mature and very advanced platform. We've even set performance levels. Even if you go into the MLPERV in further slides in detail, MLPERV is an independent benchmark for benchmarking your AI platform. So it's not an NVIDIA benchmark, it's an independent benchmark which gives you a value of how fast is this infrastructure accelerating my machine learning and deep learning environment. And we set up various world records here, so I'm going to go into that into detail, but if you take a look at the advances we've seen within the last 3 to 4 years on a Tesla K80 to train ResNet 50, it took about 25 days on a single Tesla K80. With our DGX-1 based on Volta and using the Tensor cores, we could do the same job in 8 hours. Using our DGX-2, which is the most advanced single node platform we have, incorporating 16 GPUs within a high performance network, we do the same job within 63 minutes. And using our DGX SuperPod, I'll explain what the DGX SuperPod is in a few minutes, we can do the same task in under 2 minutes. So we went from 25 days to under 2 minutes in only 4 years. Those are advances you're not going to see anywhere else. Okay, we have an end-to-end software stack, so we support all these leading frameworks and machine learning applications. And of course, it's available from everywhere. All the leading OEMs support our GPUs within their server infrastructure, and you can also access this processing power, of course, in the cloud by using the global cloud services. Okay, let's go into this first step. What is DGX? What is DGX-2? DGX SuperPod? I'm going to explain the DGX data center. What you see here is our own cluster, or a portion of our own cluster, let's say. We basically have to have two clusters, two own clusters. The cluster number one we have is Saturn V. It's called Saturn V. And we started with 125 DGX-1 nodes, still based on Pascal. That was the initial installation we had 3 years ago. We then upgraded to Volta. We then upgraded to 600 DGX-1s. We're now at, I think, 1,200, 1,300 DGX nodes within a single cluster. And with the DGX-2, we actually built an own 96 node cluster, and this thing is what we call a DGX SuperPod. And this DGX SuperPod with 96 DGX-2 nodes, went to rank 22 in the top 500 list of the fastest supercomputers worldwide. And I do have to mention that the top 500 list is based on a benchmark which is not AI specific. It is actually only measuring the LINPACK performance, so the actual FP64 double precision performance, which is measured with the LINPACK benchmark. It has nothing to do with AI. I'll go into the AI specific benchmarks and advances we're seeing there later on. Not only do we implement our own clusters, but we also power the fastest supercomputers in the world. So rank 1 on the top 500 list is the cluster called Summit, and it achieves a performance of 122 petaflops in terms of LINPACK performance, so FP64 double precision. I think we even have a slightly higher performance on the latest top 500 list. I'll have to check that and update the slide. I think we did some performance tuning there. But the other performance value I would like to point at is in terms of AI performance. So mixed precision FP16, FP32, we have actually already reached exaflop scale. This cluster is capable of 3 exaflops of AI performance within a single cluster. And it uses 27,648 of our Volta GPUs within a single cluster. And it's not only Oak Ridge National Laboratory we're powering, it's the second fastest one, Lawrence Livermore, with the cluster called Sierra. We're powering Japan's fastest HPC cluster called ABCI. We're powering Europe's fastest supercluster, which is Pitstained in Switzerland, with over 5,300 GPUs. And we're powering the fastest industrial HPC cluster, which is the NE cluster in Italy. So this is actually what I'd like to talk about today, DGX-2. DGX-2 offers you the highest AI performance within a single node. So what we achieve here in terms of performance by using our specialized tensor cores is 2 petaflops. So we achieve 2 petaflops of AI performance within a single node. And we do that by utilizing 16 of the Tesla V100 GPUs we're using here. Each of them comes with 32 GB of memory. In total, it's half a terabyte of unified video memory you can use for deploying your networks and training your networks. So basically, your networks can now have a size of half a terabyte if you like. Please make your networks larger and more complex to be able to take advantage of this processing power. And it's not only limited to the half a terabyte you can actually place within the GPUs. The host system has 1.5 terabyte of main memory, and we can basically swap out portions of the network into the main memory and use the main memory for data placement too. So the 1.5 terabytes of the host system plus the half the terabyte of the GPU memory gives you 2 terabytes. It's 2 terabytes of total memory you can basically use within this node without having to resort to external data. And we do that very efficiently. We have a page migration unit which actually takes care of the memory placement and the automatic transfer of memory pages from the host system to the video memory system. Okay, the thing is heavy. You need 4 people or a lift to place it into the rack. It's large. It has 10 rack units. You basically place 4 of these within a single rack. But then you'll have to supply 40 to 50 kilowatts of power to it because each system needs 10 kilowatts. But this is the fastest single node system you can get for training your networks. why did we implement our own system? Not only to enter a top 500 list and do marketing around it. Of course, we optimize all our algorithms and all our libraries to be able to scale not only within a single node, but to scale on a multi-node environment too. So what we actually do is we optimize and we tune our design, and if you do a multi-node setup, you're going to have to look into networking, you're going to have to look into storage. If a DGX-2 is able to train 15,000 images per second, you have to get that data into the machine. We have SSD cache to take care of buffering, but you have to supply enough data to the machine so the machine doesn't twiddle its thumbs and stall. So you have to have a high performance storage system behind it, you have to have high performance networking, etc. We tune these and we have reference architectures to help you implement such large scale implementations. This is actually the next step, going from a single DGX-1 or DGX-2 to the next stage is what we call a pod infrastructure. And this is an example of a pod infrastructure. We've tuned a DGX-1 pod here, for example, with network and storage nodes, etc., to give you a well-balanced system which will help you train with the fastest possible performance scene. And not only that, we're working closely together with the leading storage vendors. So it's NetApp, Pure Storage, TDN, Spectrum Storage, Dell EMC. We're working closely together with all of them to implement reference installations and reference designs which out of the box will be perfect. So you don't have to worry about how do I implement. Just download a white paper from NVIDIA and we will show you what's proven and what will work out of the box. This is the superpod I was talking about. It's 96 DGX-2 2H. It's a little bit more performant than the normal DGX-2. We have a higher power level here and about 10 to 15% higher performance per node. And it'll give you a roughly over 1,500 GPUs. You'll, of course, need a megawatt of power and a megawatt of cooling, of course, too. But this will give you the tipping edge of technology if you need it. What I would also like to highlight is what is happening. The traditional HPC and the modern AI, I actually see a convergence of both. So both technologies will be converging, and we're seeing that in various examples. If we take a look at what's happening, what scientists are discovering, what scientists are working on. And it's actually using the capabilities of AI to complement our traditional HPC algorithms and get them to the best result possible in the least time needed. So using AI in a specific way gives you the possibility of getting to your results faster or better, or more efficiently. This is just an example here. If we take a look at, okay, this is the latest version. We saw 122 petaflops on the other slide. It is updated here. We have 149 petaflops of FP64 performance. But by using our mixed precision tensor cores, you can actually get a way higher performance if you use specialized libraries which will take the possibility of the tensor cores and use them with specialized mathematical libraries. And using our tensor cores, we are able to get 445 petaflops out of the same existing Summit supercluster. So let's continue with RAPIDS. What is it? Okay, this is marketing slide. Big data is driving AI. I think you're not saying anything against that. Okay, what we actually see here is we will extend what we entered into with deep learning, we are now extending it to big data analytics. And that's the whole aspect of data science, going from analytics, using traditional machine learning algorithms and methods, and regression, decision trees, graph, etc. And this is going beyond deep learning. Deep learning is a subset of machine learning, but we now support the larger field of machine learning. Okay, let's take a look at the possibilities. So the possibilities in terms of business impact. In manufacturing, it's all about increasing forecasting accuracy. In retail, it's of course increasing sales. 2% I think is still a little bit small. I think there's room for expansion there. In financial services, it's all about reduction in credit losses. It's all about predicting how will my credit taker be able to pay back the money he's loaning, for example. And in healthcare, and this is, I think, where we're going to see substantial improvements and substantial implementations. It's all about patient treatments and personalized medicine, personalized treatments. Okay, these are basically the 4 areas which we talked about. Consumer internet, where it's actually it's all down to recommendation engines, for example. In retail, it's all about forecasting inventory, forecasting production, and in financial services, it's fraud detection and predicting the liability of my loan takers or not. And in healthcare, it's better disease prediction and also better disease treatment through personalized medicine. This is marketing. I think I can skip that one. We already saw that. Okay. Let's take a look at the traditional workflow within machine learning. Within machine learning, you can actually see that we have 3 stages involved. Well, first of all, you have all the data sources. And you don't have that data all in one source. You don't have that data all in one SQL database or others. You're going to have to collect the needed data from various sources. You're going to input that into a huge data lake. This huge data lake will basically be the container which contains all information you can possibly have within your business or your company. You then have to do, and that's one of the time-consuming things you're going to have to take into aspect. You're going to have to prepare that data. So it's all about the data preparation. You're going to have to get that from the SQL databases. You're going to have to combine it. You're going to have to filter it. And after you've done your data preparation, you're going to train it using traditional machine learning methods. And then after that, you evaluate it, and then you deploy it with doing the predictions based on the trained data and inputted data you would like to evaluate. What does the normal workflow of a scientist, of a machine learning scientist, look like? The normal world here, and to be honest, before we supported machine learning with our GPUs, this was basically done on CPU-only servers all the time. So machine learning is a very typical task using hundreds of traditional servers within a computing center. And that's the workflow looks like. You see a lot of coffee cups, a lot of times waiting, etc. So we had the task of speeding this up, and this is actually what we did. So with speeding up all 3 portions of it, so the data set collection, the analysis, and the preparation and the training, we're able to let that scientist go home on time and not stay late. That's basically what we see on this slide. Let's go into the 3 steps which are incorporated within machine learning. First step is data preparation. So what we implemented here is actually we give you plugins for existing for existing open source products, or drop-in replacements of leading applications in this specific field. We have a Pandas replacement, for example, and we're working on GPU accelerating Spark, and we also have GPU accelerated SQL databases we're working on, or which are being worked on by our collaboration partners. And in this stage, what we actually do is we accelerate getting that data into the GPU memory. If we have that data in the GPU memory can be accessed at about 1 terabyte of bandwidth, which gives you a much higher performance level than you would have if you were accessing this data within a normal memory of a server. So the task here is to accelerate getting that data into the memory of our GPUs. Once it's there, we can access and manipulate it extremely fast. We have various ways of doing this, and this is one of the parts which is incorporated within what we call RAPIDS. RAPIDS is a collection of all needed and popular workflows and popular applications you've been using before. We're not inventing something new. We're taking the existing, proven workflows and open source projects and just giving you a GPU accelerated version of it. So this is an example, a healthcare example from data preparation. So you're going to have, in terms of database, you have various sources. You have a source here, for example, medication. What has this patient received in the past? This is basically a database which would probably reside somewhere within the hospital or within the record of the doctor who's treating you. Then, of course, this, for example, could be data which originates from your insurance company, the healthcare insurance company you're working with. They will have data on you. And then, of course, you're going to have data from something like this. Devices which are constantly monitoring your pulse, constantly monitoring other health values. You have to combine them. They have different time scales. They come from different sources. So the first task you have is decide which data types you need and combine them into a combined data frame with a time schedule, of course, which is adjusted to incorporate all these data values. Then you're going to do model training. And in the sense of model training, you're basically using applications like XGBoost, PCI, K-means, dbScan, for example. We've accelerated all of them. We have accelerated all of them to take the benefit of GPU acceleration. And in the visualization phase, you're probably using the leading machine learning applications like Graphis3 or OmniSky. They're also integrated within RAPIDS. So if you download our RAPIDS container, you don't even have to install anything. You go to our NGC, so our NVIDIA GPU cloud. You can download the complete RAPIDS container, and everything is pre-installed within a container. You can run using our containerized support we have on the GPUs. So it is actually a Docker container, or let's say a modified Docker container. We have a Docker environment which is called NVIDIA Docker because we virtualize the GPU, and based on the NVIDIA Docker environment, you can run these containers on any environment, NVIDIA GPU-based environment if you like. And you don't have to install a single piece of software. You just download the container. We have the prerequisites for running the container. It will work. Okay, what acceleration values will that give you? I'll just talk about two examples of customers using our technology today. One of them is PayPal, PayPal is, of course, extremely interested in doing fraud detection. They don't want to lose money. So what they actually use is our T4 GPUs. Our T4 GPUs is a specialized low-power version of our Tesla GPUs to be used within standard servers. And they've been able to improve the real-time fraud detection by 10%. 10% doesn't sound like much, but we're talking about fraud detection. Getting that value up 10% is worlds of performance. And then they've been able, by using the same servers, been able to get 8 times the throughput. 8 times the throughput by using GPUs. Next one, and this retailer doesn't want his name to be mentioned, but I know who it is. They've used RAPIDS with CUDA-DF, and the problem they had is inputting that data to do the machine learning on it. And by deploying our specialized CUDA-DF, the specialized version for data inputting, they were able to achieve 2,000 times speed up, 2,000 times. And now they don't have this limitation anymore. The limitation they had was preparing everything to analyze it. Now they can analyze it several times a day. Another example, XGBoost on DGX-1, 10 to 20 times speed up with the Chinese company BGI doing cancer treatment, personalized cancer treatment for patients. Next one is also using XGBoost and Pandas, and they've achieved substantial speed ups too, 6 times speed ups, and we're talking about comparing a single server node against a single GPU. If you put that into a DGX-1 or DGX-2 content, then of course it's 8 times or 16 times the 6-fold speed up you're seeing here. Another example, also from the Chinese market, big quant, they're seeing 6 times. So 6 times seems to be at least the speed up you're going to see. And here we have a benchmarks showing the speed up of one of the 3 steps we have in the workflow. So in terms of CUDA-IO and CUDA-DF, so the load and data preparation, comparing it to standard CPU nodes, we see the speed up of a DGX-2 and the speed up of 5 times a DGX-1. So we also see the scalability over multiple nodes here. And if you compare these numbers, this is exponentially speed up. Same thing applies to acceleration of XGBoost. And you see the difference between using a single DGX-2 and using 100 dual socket traditional nodes. That's the speed up you're going to see. So it's something like 12 times speed up. And same thing applies if you take the whole workflow, adding all these individual steps. We're accelerating each step. If you have the aggregation of all 3 steps within the machine learning, you see the substantial speed ups we achieve comparing 20, 30, 50, or 100 traditional nodes. So, in the end effect, the question you're going to have to ask yourself in the end is, do I do it the traditional way? And this is a benchmark based on the Fannie Mae mortgage data. It's 192 gigabytes of data, collected over 16 years with 68 quarters, and it has 34.7 million single-family mortgage loans in it. And this is the data you need for training. And what you actually train here with XGBoost, you train 50 individual features, and you train a network so that you will be able to predict this loan taker who is sitting in front of me, is he going to pay back the money I'm giving him or not? How high is the percentage that I will see my money again? And to train this, you can actually take 300 servers, traditional servers. They'll cost you about $3 million US, and they consume 180 kilowatts, and you'll need a lot of space for that, or you do it this way. You do it this way with one single DGX-2, this is this thing in the rack, only 10 kilowatts of power needed, 1/8 the cost, 1/15 the space, 1/18 the power. You decide what you like to do. A single DGX-2 is able to do the same task in the same time. If you want more detailed information and also our blogs on this topic, I advise you to go to our data science subpage on our network, or we have a specialized web link called www.rapids.ai, and this is where you will see all the latest information on RAPIDS and also be able to download the RAPIDS container to start. A few words on MLPERV. I was talking about MLPERV. It is an independent benchmark, and the benchmark is supported by these leading companies. So all these companies are supporting companies of the MLPERV. And MLPERV is an independent benchmark so that you are able to evaluate a specific machine learning and deep learning accelerating infrastructure and be able to compare various different implementations of that. There are basically various tasks which are defined within these benchmarks. It's image classification using ResNet 50 and using the ImageNet dataset, of course. Then we have object detection, two versions, a lightweight and a heavyweight version, using these networks and the same COCO data set. Then we have translation, recurrent and non-recurrent, using two various networks for that. And the database is English-German. I always knew German wasn't a simple language. Now I have the proof. And we also have a task of a recommendation engine using Movie Lens 20 million benchmark data set. And then we have the other task is a reinforcement learning on the Minigo network. All of these are the single tasks which are defined within this benchmark, and you have to run them all. This is the single node performance values we got. They were all, the performance values were achieved by a single DGX-2H. DGX-2H is a somewhat overtuned DGX-2, let's say. And these are the values we achieved here. All leading values, world records. No one's faster. And there's also a second portion of the ML benchmark, which where you can scale multi-node. So you're not limited to a single node, you can scale multi-node. And also for this, we have achieved these benchmarks. And it's basically also based on portions of our Saturn V cluster, which we have implemented on our own site. Okay, this maybe one word on mixed precision. How do you deploy mixed precision? If you don't tell the framework that you want mixed precision used, it's not going to use it by itself. But by adding 2 additional lines of code, we are supporting already 3 deep learning frameworks, which will try to do that automatically. By just adding 2 lines of code, you can actually have the deep learning network decide when to use FP32 single precision, or when to use mixed precision FP16, FP32, which will give you the substantial speed up by deploying our tensor cores. And you can do that whilst training, or even better, whilst inferencing. Also in inferencing, you'll basically see a 2 to 3 times speed up in performance in inferencing too. If I have 5 minutes, I'd like to show a few slides on what do we do on the edge and why is edge computing so important for us. So what we've looked at the moment now is data center. We've taken a look at data center where you basically have your Tesla and your DGX and you do your model training and your simulation. But what do you do in a robot if you're deploying it and this robot doesn't have a link to your data center and has to do that autonomously by its own? You're going to have some kind of infrastructure within the device, within the car, within the robot, within that flying drone, which will be able to make the decisions needed in real time. And the interesting feature is, of course, we are using the same software stack, regardless if it's in the data center or if it's in the edge device. You will use the same software stack, and we even have specialized ways of optimizing your inference engine by using, for example, TensorRT. TensorRT is our runtime environment, but it's not limited to TensorFlow alone. Using the common definition framework, output capability of every deep learning framework, you can use our TensorRT to basically pre-compile and optimize your network. And then you're able not only to use it within the data center, and here we have our TensorRT capability, but you can use it in your embedded or automotive. In embedded, you're going to use our Jetpack SDK on our embedded systems. And in terms of automotive, you're going to use the DriveWorks SDK on our specialized Drive PX products within autonomous driving vehicles. Just a few examples. Why does the edge matter? Well, maybe it's a question of bandwidth. If you have cameras, a billion cameras worldwide with tens of petabytes per day, you're not going to transfer that data into the data center to have it analyzed. You don't have that bandwidth to do it. Then it's, of course, all about latency. If you're evaluating 30 images per second and you have a maximum latency of 20 milliseconds before that robot does something stupid, you have to do it you have to reach that decision within a specific point of time. If you don't have the decision by then, nothing's going to happen. So if you have latency with transferring that data to a data center, that's not going to work either. Same thing is privacy, confidentiality. Do you want that data to be transferred over public network or not? You have workflows where you don't want to have it transferred. And then, of course, it's all about availability. In the middle of the desert, you don't even have any mobile net. You're not going to have any possibility of transferring data. You have to do that decision. And on Mars, for example, you're going to have to do that decision in real time without transferring that data to Earth. Just one example, Blue River. They were actually acquired by John Deere recently. So that's the tractor, and that's the device we're talking about. And what they do here is, you can say 90% of herbicides, if you are able to detect in real time by imaging what is my harvest and what's my weed, and I only spray that herbicide on the weed, if I'm able to do that in real time, and that's why they have these large boxes on top. This is mobile AI platforms deciding where to spray that herbicide, and not just spraying it everywhere. Spraying it only on what is detected as weed only. And by doing that, we're going to lead to a more greener world, of course. We save 90% of herbicide. This is what we introduced recently. I call it, this is the building block of an AI researcher or a robot builder. It's a small device, but it's capable of quite a lot of calculation. So I actually would also even call it the Raspberry Pi of AI. I call it the Raspberry Pi of AI. Raspberry Pi is good, but when it comes to AI, Raspberry Pi lacks performance. And if you do inferencing, this is the Raspberry Pi of AI you're going to be using. $129 US. It comes in a 5 watt and 10 watt flavor. Has 128 CUDA cores and a 4-core ARM-based CPU. Is capable of handling 8 high-definition video inputs in parallel. That can be done by this small device. We have a demand on this from universities within Europe who would like to build their own courses based on this product for training and for education purposes. This is the perfect fit. Okay. To further support building environments and training robot environments, we also have something which is called ISAC. The ISAC is actually a physically correct simulator which is able to simulate the robot or other device which you are just developing. And you can actually train it in this simulation. And the interesting thing is you can train it 1,000 times in parallel, and you can train it at maybe 10 times actual speed. So you're not limited to doing that physically. And the same thing applies for training autonomous driving vehicles too. If you have cars traveling on the road, they will collect data for you, but only in a limited quantity. Even if you have 100 cars on the road, I know BMW and Audi, they have several dozen cars traveling on the German Autobahn. I see them almost every day. And, but they only collect a limited amount of data you need. If you need more data, you have to do that in a physically correct simulation where you can do that 1,000 times in parallel and at 10 times real speed, real world speed. If you're able to do that, you're going to come to your training result much faster, and you'll be able to supply that data needed even by using data coming from simulated worlds. We simulate worlds really good too. Using that, we are quite sure that the autonomous driving vehicle of the future will be based on 10 to 15% real world data, and the rest will come from reality virtual environments, which we will simulate too. So our GPUs will be doing both. They will be simulating real worlds and ray tracing and rendering that, and using that input data for training larger networks, which will do a specific task like driving a car. Okay, I'm going to skip this one. Okay, then I'm at the end of my presentation. Hope you enjoyed it and open for questions.